This is my intermediate algebra course. Today we're going to continue to learn applications of algebra. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. In the previous class, we learned the special number e, and we used it as a base in exponential expressions. We found that that number is useful in finance, but you're also going to learn in future courses. We don't have time in this course, but you're going to find that that number is useful in science. It has a lot of applications in the real world, and so we give it special notation when we use the number as the base in a logarithm. Log base e of x is abbreviated as lnx, which stands for natural logarithm, or natural log x. And it's called natural logarithm because it's used, like I said, in nature. But we also use 10 as a very common base in exponential expressions and also logarithms. But we use base 10 for a different reason. We use base 10 simply because it makes the numbers easier to work with. Our number system has 10 symbols, which makes the number 10 a very convenient base for exponential expressions and logarithms. So we have abbreviated notation for base 10 logarithms. Log base 10 of x is abbreviated log x. So whenever you see a logarithm and there's no base written, that base is assumed to be 10. So here's some examples. Log base 10 of 3 is log 3. Log base 10 of 8.2 is log 8.2. It's just an abbreviated way to write those logarithms. Log base e of 2 is ln 2, and log base e of 8 over 7 is ln 8 over 7. So let's do some examples here. It says write the abbreviated forms of the logarithms below. Log base 10 of 562 can be abbreviated as log 562 or log 562. Log base e of 0.9 can be abbreviated as ln 0.9. Again, these are special bases. And log base 10 of pi can be abbreviated as log pi. Again, if the base is 10, then you can just write log of whatever that number is in the function. And log base e of 4 over y you can write as ln 4 over y. So I want you to try number 5. Actually, go ahead and try 5 through 8. You can do all those problems. And when you come back, we'll do them together. Okay, we're back. Log base e of 8,000 is ln 8,000. Log base 10 of 2 over 3 can be written as log 2 over 3. Be sure to write parentheses around the fraction. Log base e of x squared can be written as ln x squared. No parentheses needed in that case. And log base 10 of 3y can be written as log 3y. You do need parentheses there, though. So if you got those right, good job. So now let's go on to some exponential equations that have these special bases. Now, we've done these problems before in this course. We just haven't seen these special bases. So let's try number 9. We did problems where we had, for example, base 2, and we had to use exponent rule number 1. and we would add the exponents. But now we have base e. Remember, e is just a constant. It's just a constant number. We're going to use the exponent rules just like we would when you have a number as the base as opposed to a letter. We have the same base, so you're just going to add the exponents. So we get x plus 3x. So 7 is equal to e to the 4x power. So at this point, we're stuck. We need a calculator to help us figure out what the exponent is going to be. If you raise this special number, e, which is 2.718, on and on and on, if you raise that special number to some power and get 7, what is that power that you raise the e to get 7? Well, we need advanced mathematics. And so we need to use the calculator. The calculator can do advanced mathematics for us. So the power, or the exponent, is equal to log base e of 7. This is just how you would write the notation. But remember, log base e has special notation. If you try to enter this into the calculator, it's going to be very difficult. So mathematicians have a special button, an ln button. So instead of writing log base e, you're just going to enter in ln in your calculator. But before we do that, let's go ahead and divide both sides of the equation by 4, because we're not looking for 4x, we're looking for x. So we get natural log 7 over 4, and that's going to be the final answer. Now, you could leave that as your answer, but it says up here, round to the nearest thousandth. So I'm just going to go ahead and calculate. And if you're using an iPhone, you want to enter 7 and then push the ln button right in the middle if you're in landscape mode. So we get x is approximately equal to 1.9459. It just goes on and on over 4. So then we're going to divide that number by 4 and we get our final answer. So I'm going to go off to the side here. We get 0.486, and it says round to nearest thousandth, so that should be good enough. Okay, let's try another one of these problems before you try one on your own. So now we have base 10. In the previous problem we had that special base e, now we have the special base 10, but it's no difference. Really the same type of problem. I guess we don't need two divider lines. So we're dividing powers, so we're going to use exponent rule number 2, which means that we're going to subtract the exponents. And the only reason we can do that is because the exponential expressions, the green and the blue, they have the same base. So that was exponent rule 2, and 7x minus 5x is 2x. So now we're stuck. We don't know what to do here, because this is going to require advanced mathematics to figure out what we raise 10 to get 8. But our calculator can do those calculations for us. But we have to know what to enter into the calculator. So we're going to enter log base 10 of 8. But remember, because this is base 10, your calculator is going to have special notation. So instead of writing log base 10 of 8, we're just going to write log 8. That means the same thing as log base 10. So now we're going to divide both sides by 2, and in your calculator you're going to enter 8, and then right in the middle it says log base 10, or your calculator might just say log, So push log or log base 10 depending on what you're using. And we get 0.903, and it goes on, and that's still divided by 2. So I'm going to move this over. Then we have to divide that by 2. So divided by 2 equals, and then we get our final answer. So 0.452. Remember, they tell us to round to the nearest thousandth. Okay, so you can take a picture of all this to help you. And I want you to try 2 of those problems on your own. So try number 11, and when you come back, we'll do it together. Okay, we're back. We're going to use exponent rule number 2. We have the same base, so we can combine those exponential expressions. Then we get e to the 5x is equal to 3, and at that point we're stuck. We can't really do anything unless we use advanced mathematics. Your calculator can do advanced mathematics, but the problem is you need to tell your calculator what to do. So what do we tell the calculator? We tell the calculator to find log base e of 3. The problem is your calculator uses abbreviated notation for log base e of 3. It uses ln 3. So now we just divide both sides by 5, and we get ln 3 over 5. That's really the final answer, but let's go ahead and enter in 3 to our calculator and push ln. And by the way, if you're using a Texas Instruments calculator, you're going to have to push ln first, then 3. And we're going to divide that by 5. I'm not rounding off the number, so if you can, avoid rounding off at all. Divide by 5, and we get 0.21, actually 0.22 if we round off properly. I'll add a 0 there just to show we rounded off to the nearest thousandth. Okay, so if you got that answer, excellent. So why don't you try number 12, and when you come back, we'll do it together. Okay, we're back. So we're going to use exponent rule number 1. We're multiplying powers, which means that we add the exponents. So we get 10 to the 3x is equal to 18. At this point, we're stuck. We don't really know how to calculate the exponent that would make this equation true. So we go to the calculator, and it's going to be log base 10 of 18. That's just how you enter it into the calculator. But remember, your calculator has special notation. When the logarithm has a base 10, it just becomes log 18, log 18. And then we're going to divide both sides by 3. So I'm going to enter 18 in my iPhone. Remember, if you're using a graphing calculator, you're going to have to push the log button first, then 18. But if you're using an iPhone, you enter 18 and then push the log base 10 button. So we get 1.25527, and it just keeps going on and on. I'm going to keep that exact number in my calculator, divide by 3, and our final approximation is 0.418. So if you got that answer, excellent. Very, very good. If you made a mistake, that's okay. It's okay to make mistakes as long as you go back and figure out what you did wrong. So let's go on to some more of these types of problems. We have an exponential equation where the strategy in this case is just going to be to isolate the exponential expression. It's not isolated right now because the 2 and the negative, or the positive 1, I should say that's a negative 2 and a positive 1, they're in the way. So we have to get rid of those. Not get rid of them, but put them on the other side. So I'm going to subtract 1 from both sides of the equation. And because this can be kind of confusing for students, I'm going to go ahead and show the division. We're dividing both sides by -2 at this point. That can be kind of confusing for students. Remember, when you have a number right next to an exponential expression like this, that means the number is multiplied. The green is multiplied by the purple. That's just how the math notation works. So now we have 9/2 is equal to e to the x, and we're stuck. We don't know what to do at this point. But the equation is much simpler. But remember, when we're stuck, that means we go to the calculator. And the calculator, we're going to write log base e of 9/2. The problem is that's very difficult to enter into the calculator. So we use special notation. We say ln 9/2. So again, if you're using a TI or any kind of graphing calculator, you're probably going to push the ln button first. But in your iPhone, you're going to enter 9 divided by 2 and then equals. Then you're going to push the ln button. And we're going to get 1.504. So that is the final answer. Okay, let's try one more of these before you try one on your own. To solve this exponential equation, we're going to isolate the exponential expression. It's not isolated because the 6 and the 4 are next to it. So we're going to put the 6 and the 4 on the other side of the equation. So I'm going to subtract 4 from both sides. Then I'm going to divide both sides of the equation by 6. Now again, students are going to have a lot of trouble with the idea that this yellow 6 is multiplied by the green 10 to the x. That's just how the math notation works. Those two are multiplied together, so that's why I had to divide both sides by 6. And maybe I should go ahead and show that. Students typically have a lot of trouble with that. It seems easy, but the confusion comes in really with the notation. That's the way it is with math in general. If you're going to have problems, it's probably going to be caused by not understanding what the notation is telling you to do. So at this point, we're stuck. We have to use advanced mathematics. So what do we tell the calculator? We tell the calculator log base 10 of 2. It's just a way to tell the calculator how to figure out the answer. But remember, in a calculator, we don't write the log base 10 of 2 because that's a special base. We write the abbreviated log 2. So it's different depending on what kind of calculator you have. If you have a graphing calculator, you're going to write log or enter log first, push the log button. Then you're going to enter 2. But if you have an iPhone, you're going to enter 2. Then you're going to push the log base 10 button in the middle in landscape mode. So there you go. Now you should be using a graphing calculator. If you have a graphing calculator, please use that. Because remember, in school, if you want to prepare for college or prepare for college entrance exams or prepare for any kind of math exam in school, your teacher is not going to allow you to use your phone. So you may become proficient using your phone, but it's not really going to matter if your teacher doesn't allow you to use your phone. So you need to use a graphing calculator. So go ahead and take pictures of these two problems. They're going to help you with numbers 15 and 16. So go ahead and try number 15. Remember, you want to isolate the exponential expression, which means you want to get rid of the 3 and the -1. When I say get rid of, I mean put it on the other side of the equation. Try number 15. When you come back, we'll do it together. Okay, we're back. We're going to add 1 to both sides of the equation. Then we're going to divide both sides by 3. And I'm going to show that because, again, that can be a source of confusion for students. at this point we're stuck. We don't know what to do. We can't really calculate this. But remember, your calculator can do that for us. So we have log base e of 4. But again, there's abbreviated notation for these special bases. So log base e of 4 can be written as ln 4, and that can be approximated. In my iPhone, I'm going to enter 4 and then the ln button, and I get 1.386. Now again, if you're using a graphing calculator, it's going to be very, very different. Okay, so I want you to try number 16, and when you come back, we'll do it together. Okay, we're back. I'm going to subtract 7 from both sides. Then I'm going to divide both sides by 5, and I'm going to show that because, again, students have a lot of trouble with that notation there. So now we have 7 over 5 is equal to 10 to the x power. And at that point, we're really stuck because we need the calculator to help us. That's okay. All we have to do is enter log base 10 of 7/5, and the calculator will tell us what to do. But remember, your calculator doesn't use a 10 in the notation. When you have a log, we're trying to find the value of a base 10 logarithm, you just write log of whatever number, log 7/5. So if you're using a graphing calculator, you need to be careful because we have a fraction inside the logarithm. So you're going to need to use parentheses and be very careful. So I'm going to enter 7 divided by 5 in my iPhone, and I get 1.4. Then I'm going to press log base 10, and then we have the answer. So it is approximately 0.146. And there you go. So if you got those answers, excellent. Okay, so now we're going to solve logarithmic equations. In the previous problems, we solved exponential equations. Now we're going to solve logarithmic equations because they have logarithms in them. So what I need to do in these problems is I need to isolate this logarithm. So I'm going to add 5 to both sides. And then I'm going to divide both sides by 2, because that's 2 times log base 10 of x. At this point, we're stuck. We don't know what to do. We don't know what's going on here. But if we know what this notation means, we can figure things out. First of all, we need to ask, what is the base? Well, that's a big problem because I don't see a base. There is no number here. But remember, when you don't see a number there, that means base 10. That's the whole point of us doing this, is for you to get used to that abbreviated notation. So now we know the base of an exponential expression is 10. The exponent is whatever the logarithm is equal to, and whatever's in the log function goes on the other side of the equation. Well, now we're done. If you want to, you can write the answer as 100,000. If you raise 10 to the 5th power, you get 100,000. But you can probably keep your answer as 10 to the 5th. I don't really prefer one way or the other. So again, we've done equations like that, but we never did equations that have a special bases. We have a base 10 logarithm in that problem. So now we have another logarithm with a special base. This is base e. Whenever you see ln, it means log base e. So I'm going to subtract 15 from both sides. First thing we're going to do is isolate the logarithm. Then I'm going to multiply both sides by -3, and maybe I should show that just so there's no confusion. So I'm multiplying both sides by -3, and don't write this, that is incorrect. You must write parentheses on the -2 also, or else it'll mean subtraction. So now we get 6 is equal to ln x. But again, we're stuck. We don't know what to do at this point unless we can translate to an exponential equation. We can't translate to an exponential equation because we don't even know what the base of the logarithm is. So we have to remember that ln means log base e of x. Now we know that the base of the exponential expression that this is referring to is e. The exponent is whatever the logarithm is equal to, and whatever is inside the log function goes on the other side of the equation. Now, these problems tell us to round to the nearest thousandth. So I'm going to go ahead and calculate e to the 6th power and round to the nearest thousandth. So I'm going to enter 6 in my iPhone and then push e to the x. And I get 403.429. It's actually better to leave your answer as e to the 6 because that's an exact number, but we're just demonstrating in this class that e is just a constant. It's very important. In fact, more important than anything else for you to understand that e is just a constant. It's just a number. So that's taking 2.718 and it keeps going on, and we're raising that to the 6th power to get 403.429. Okay, so I want you to take a picture of those problems, or well, the best thing is take a picture with your phone. You can take a screenshot. You're going to need those problems as we go along. And I want you to try number 19. And when you come back, we'll do it together. Remember, you want to get this ln by itself on one side of the equation, which means you're going to take the -21 and the 4 and put it on the other side of the equation. When you come back, we'll do it together. All right, we're back. I'm going to add 21 to both sides of the equation. Then I'm going to divide both sides by 4. So I get 1 is equal to natural log x. But I don't know what ln means, so I'm going to change it to log base e. Well, now I have a chance to figure out what is going on here. Remember, you can't solve a logarithmic equation unless you convert to the corresponding exponential form. So the base is always that small number. The exponent is whatever the logarithm is equal to, which is 1. And what's in the log function goes on the other side of the equation. So I'm going to write the final answer as an abbreviation. Well, first of all, e to the 1st power is just e. So I'm going to write e, that is exponent property 6. And then I'm going to approximate. So on my iPhone, I'm going to enter, well, there's actually an E button at the bottom middle and landscape button. I'm just going to push that E button, and we have 2.718, and that's it. So if you got that problem right, excellent. Okay. So go ahead and try number 20. When you come back, we'll do it together. Okay, we're back. I'm going to add 1 to both sides of the equation. Then I'm going to multiply both sides by 5. And at this point, we're stuck. We don't know what to do. But remember, log x means log base 10 of x. So now we have some clues as to what to do. We can translate to an exponential equation. The base is 10, the exponent is 0, and whatever's in the log function goes on the other side of the equation. Well, 10 to the 0 power, that's going to require exponent rule 7. And anything raised to the 0 power is just 1. So we're done. That's it. So if you got that one right, excellent. Now if you forgot to write these exponent rules, that's okay. We didn't have to write exponent rules on these previous problems. But those are the rules that we're using. So now let's go on to number 21. Now we're going to be doing more logarithmic equations, solving logarithmic equations, but they're going to be a little more complicated, so we have to use some logarithm properties. So this equation is asking us to find x, but the equation is too complicated for us to find x right now. So we have to simplify it. We have to combine those logarithms using this rule here, but we're kind of going backwards. We're starting from the right and going to the left. So we're going to combine those logarithms, but before we do that, remember there's no subscript written in those logarithms, so that means log base 10. So now we know the base. Remember, this property doesn't work unless the bases of the logarithms are the same. So we need to really specify that first. So now we can combine the logarithms and we multiply what's inside the logarithms. And at this point, again, we're going to be stuck unless we know how to translate a logarithmic equation to an exponential equation. The base is 10, the exponent is whatever the logarithm is equal to, and whatever's in the log function, that goes on the other side of the equation. 10 to the first power is 10, of course, and that is exponent rule number 6. And then we're just going to divide both sides by 2. So dividing both sides by 2, we get x is equal to 5. So again, we have to use some of these logarithm properties that we learned in previous classes. And by the way, I forgot to write the logarithm property. Let's go ahead and write L for logarithm property, and then Roman numeral 5, logarithm property 5. Okay, let's try number 22 before you try one of these on your own. So the first thing we need to do is unravel the mystery. What are those ln's? Well, they are log base e. Now a lot of the mystery is going away. And now we need to simplify the equation by combining the logarithms. Well, that's logarithm property 6. They both have the same base e. So we can combine those logarithms to log base e of x over 7. Now we're dividing. In the previous problem we multiplied because we were adding the logarithms. Well, now we're subtracting, so we're dividing what's inside the logarithms. So now we're stuck. Unless we know how to translate a logarithmic equation to an exponential equation, we can't really do anything from this point. But we know that that little subscript is always the base of the exponential expression. Whatever the logarithm is equal to, that's always the exponent. And whatever's inside the log function, that goes on the other side. And by the way, that was logarithm property 6. So I'm going to write L Roman numeral 6. So then we're going to multiply both sides of the equation by 7, so we get x is equal to 7 times e to the third power. And remember, it's so important to remember that e is just a number. That's all it is. So I'm going to enter 3 and then push e to the x on my calculator. And again, if you're using a graphing calculator, which you should be doing, then you're going to have to enter e to the x first, and then in your box you're going to plug in the number. So we have 7 times 20.085, and it just goes on and on. So then I'm going to multiply that by 7 times 7 equals, and we get 140.599. So there you go. Okay, let me bring this up. All right, so now it's time for you to try. Go and attempt number 23. You have your logarithm properties up there. And when you come back, we'll do it together. Okay, we're back. So we're going to use logarithm property 7 because we're subtracting the logarithms. That was the property we used in the previous problem. And by the way, before we do anything, let's go ahead and figure out what the base is on those logarithms, because we have to make sure it's the same base. Well, obviously, if there's no base written, it's assumed to be base 10. So now we know that those are the same base, that logarithms have the same base, so we get the equation there, and we have to translate. So the base of the exponential expression is 10, the exponent is 3, and again, that's just how you translate from a logarithmic equation to an exponential equation. So now we get 1000 is equal to x over 8, and we just have to multiply both sides by 8, and of course our final answer is 8,000. So if you got that answer, perfect. Okay, go ahead and try number 24, and when you come back, we'll do it together. Okay, we're back. So our first question is, what is the base? We don't know what ln means, but if we translate, we can see that those ln's are just base e logarithms. And now we can use logarithm property 5, which tells us if we're adding logarithms that have the same base, we can just combine those logarithms to one logarithm. And inside our one logarithm, we have the product of the numbers inside the previous logarithms. Well, now we're stuck unless we know how to translate from a logarithmic equation to an exponential equation. The base is always that subscript there. The exponent is always what the logarithm is equal to, and whatever is inside the log function goes there. Well, now we're going to use exponent rule 9 to figure out what 1/2 power means. That means square root e. Remember that? So now we're going to divide both sides by 3. I'm going to go ahead and flip the equation around. So we have x is equal to root e divided by 3. So in my iPhone, I'm going to push the button in the middle, E. Then at the left, middle left, I'm going to push the square root button. So I get 1.6487, and it just keeps going on and on. Then I'm going to divide that by 3, and we got our answer. So our final answer is 0.55. That is our final answer. I don't have much room there, so if you got that answer, excellent. Okay, so now we're just going to do some slightly more difficult problems, because these problems are going to require logarithm property 7, which we have not used yet. In order to solve this equation, I want to combine these logarithms and simplify the equation, but I can't combine the logarithms because the 4 is in front of this logarithm. Those previous properties don't tell us what to do when you have a coefficient in front of the logarithm. So I'm going to use this property up here. But before I do that, we first need to figure out what the base of these logarithms is. And of course, there is no base written, but that means log base 10. So now I'm going to use this property up here. I'm going to take 4 and throw it up into the exponent. And then I'm going to use, and I should write that down, so that's logarithm property 7. Again, that's that property up there. Then I'm going to use logarithm property 5. So log base 10 of 9x to the 4th is equal to 2. So now we have to translate to an exponential equation just like we did in the previous problems. And 10 to the second power is 100. Then we're just going to divide both sides by 9, and we get 100 over 9 is equal to x to the 4th. And we want to find the 4th root of both sides. But because this is an even exponent, we have to write plus or minus. So that means that there's two solutions. X can be equal to positive 4th root of 100 over 9, or x can be equal to negative 4th root of 100 over 9. The problem is, remember, we're not allowed to have a negative number as the input in this logarithm at the beginning of the problem here. We're not allowed to have a negative inside that logarithm. It can be part of the operations inside the logarithm, but once you get your final number in there, it's got to be a positive number. So this number here is an extraneous solution, so we don't rectangle that. That's not a solution. So there's only one solution to this problem. I guess we can go ahead and estimate what that will be. So 100, I'm going to enter 100 divided by 9 equals, then I'm going to push, it's the middle left in landscape mode of your iPhone, it's the y-th root. It says y square root x. So I'm going to push that, and I'm going to push enter 4 equals, so x is approximately equal to 1.82 6. So again, these problems tell us to round to the nearest thousandth. Okay, so let's try one more of these before you try one on your own. Again, we've done these problems before, but now we're getting used to these special bases and the notation used. So the first question we want to ask is, what does ln mean? Well, it means log base e. So now we want to simplify this equation so we can solve it, and we want to combine the logarithms into one logarithm, but we can't do that because this 1/3 is preventing us. It's not part of logarithm property 6. There's no coefficient in logarithm property 6, so we don't know what to do, but we can use this property up here, logarithm property 7, to take that 1/3 and throw it up so it becomes an exponent. So this whole green expression here became the blue expression. We took that 1/3 and we threw it up into the exponent. Completely legal. Doesn't seem like it's legal, but it is. Now we're going to use, and by the way, that was logarithm property 7. Now we're going to use logarithm property 6. When you're subtracting logarithms that have the same base, you can combine into one logarithm. And now we need to translate to an exponential equation so we can see what's going on here. So the base is e, the exponent is what the logarithm is equal to, and whatever's in the log function goes on the other side of the equation. Now this can be a source of a lot of confusion for students. And why is that? Well, because the variable is in the denominator of the fraction. Students really get confused in that situation. So I'm going to rewrite e to the second power. I'm going to rewrite the whole equation actually. And there's a lot of different ways to do this problem, but when it comes to educational value, when it comes to understanding what's going on here, the best thing to do is multiply both sides by x to the 1/3. So now we have e squared times x to the 1/3 is equal to 10. And then we're going to divide both sides of the equation by e squared. And the whole purpose of this is to get x by itself. So now we have x to the 1/3 power is equal to 10 over e to the second power. So all of that work there can be quite confusing for students, but it's really just basic math operations. If you don't know how to solve an equation like this, well, now you do. That's the easiest way to do it. You're just multiplying both sides. But again, you can flip both sides, you can cross multiply, you can do a lot of different methods, but this is the method that's really going to be the best when it comes to educational value, understanding what algebraic operations are actually occurring. The problem is we have an x to the 1/3 power at this point, and we don't know what that means. So we use exponent rule 9, and that tells us that that is the same thing as the cube root of x. So now we have an idea of what to do. All we have to do is cube both sides. We're going to cube both sides of the equation. And that's going to counteract the cube root. So we're going to have x is equal to 10 over e squared, all raised to the 3rd power. Now that's a lot of stuff to enter into your calculator. It's not going to be easy, especially if you have an iPhone. If you have a graphing calculator, you can actually find a fraction template, and you can enter that right in there. But if you're using an iPhone, we're going to enter 10 divided by, then we're going to press 2, then we're going to press e to the x button, then we're going to enter equals, and you're going to get 1.35333. Then you're going to push the x cubed button at the upper left, x to the 3rd power, and you get your answer. So I know that that's a lot. That's kind of confusing to have to enter all that stuff. But you have to get used to your calculator eventually, so it might as well be now. So we have 2.479. Okay, so now it's your turn. I want you to try number 27. The first step is to figure out what base we're using in these logarithms. So go ahead and try 27. When you come back, we'll do it together. Okay, we're back. These are base 10 logarithms. I know that because there is no base written. When there's no base written in the logarithm, that means base 10. Now I want to combine these logarithms, but I can't because we have that 3 there. So I'm going to use logarithm property 7, take that 3 and throw it up. And then I'm going to combine those logarithms. Using logarithm property 5. And now we're really stuck. Unless you know how to convert from a logarithmic equation to an exponential equation, you're not going to know what to do. This is all about notation. What is the base? What's that subscript there? What is the exponent? Well, it's whatever the logarithm is equal to. And what goes on the other side? Whatever's in the log function. If you don't know how to do that translation from a logarithmic to an exponential equation, then you're just going to be stuck. And you're not going to be stuck because you don't understand the concepts. You're going to be stuck because you don't understand the notation. Math is all about learning how to read and write the symbols. You either learn or you don't. Okay, 10 to the second power is 100. Then we're going to divide both sides by 2. And maybe I should show that division. So dividing both sides by 2. And then we're just going to cube root both sides. So we have cube root 50 is equal to x. And it's probably best just to leave your answer like that, but we're going to go ahead and round off because the problem tells us to round. So I'm going to enter 50 and then the cube root button at the middle left. And I get approximately 3.684. Okay, so if you got that one right, excellent. Okay, try number 27, or excuse me, try number 28. And when you come back, we'll do it together. Okay, we're back. So our first task is to try to figure out what type of logarithms these are. ln means log base e, so these are base e logarithms. And then we're going to use logarithm property 7 and throw that 2 up, because we can't combine these logarithms unless we move that 2. So that was logarithm property 7. And then we're going to use logarithm property 6 because we're subtracting the logarithms. So we have log base e of x squared over 6 is equal to 0. So the base is e, the exponent is whatever the logarithm is equal to, and then we have x squared over 6 on the other side. Now we have to use an exponent rule. Using exponent rule 7, we know that anything raised to the 0 power is just 1. Then we're going to multiply both sides of the equation by 6. Then we're going to square root both sides. But the biggest mistake that students make, or one of the biggest mistakes, is they forget to write plus or minus because this is an even power. When you have an even power, you have to write plus or minus. Over here, we didn't have to do that because we had an odd power. But remember, one of these solutions might be an extraneous answer, meaning it's not actually a solution. And sure enough, this negative number, if you plug it into the original logarithm, we get a negative as that number in that logarithm, so that's not allowed. So that's an extraneous solution, so I'm going to put a slash through that. And I'm going to use my calculator to find the final estimation or final approximation. I'm going to enter 6 and the square root button at the middle left. And we get 2.449. All right, if you got that answer, excellent. Okay. So we used that special base E, Euler's number, in finance. And we're going to learn in future courses that we can use it in science too. But we're now going to learn some applications of base 10 logarithms. And testing the acidity of water is one application. And you've probably heard of pH. pH is a measure of the acidity of water. If you've bit into a lemon has a citrusy taste. That means it's slightly acidic. If you've drank milk, then that's a basic taste. And the concentration of hydrogen ions is a major factor in determining how acidic a solution is. So we're going to measure the hydrogen ion concentration. The problem is hydrogen ion concentration is measured in numbers that are fairly small. And notice here it says hydrogen ion concentration is measured in moles per liter. Now, what is a mole? Well, there are so many trillions and trillions of these molecules that we use a special number called a mole, which makes it easier for us to calculate. For example, when you go to the donut shop, you might say, I want 2 dozen donuts, rather than saying I want 24 donuts. So we're going to use moles, but even using that number, the hydrogen ion concentration is still very, very small. These are small numbers. So in order to measure acidity with numbers that are easier for us to deal with, we use base 10 logarithms. Again, the whole purpose of a base 10 logarithm is to make the numbers easier to work with. So in chemistry, hydrogen ion concentration is notated with a bracket and an H plus. H stands for hydrogen, plus stands for ion. You'll learn about that in chemistry. You don't need to worry about that now. But as you can see up here, pH is defined as the negative log base 10, negative log base 10 of the hydrogen ion concentration. So I know that sounds kind of confusing, but it's really easy. pH is equal to negative log of the hydrogen ion concentration. Now, in math, brackets are used for various reasons, but in chemistry, these brackets are actually part of the notation, so I don't mean to confuse you by that, but just consider this whole expression to be the variable. Now, the reason we write the negative symbol is because our answer is going to end up being negative in most cases. So in order to, again, make the numbers easier, we're going to switch it to a positive with the negative symbol. That's just how pH is defined. Again, this is all just to make the numbers easier for us to consider. So we don't know what the base is because there is no base written. But remember, when there's no base written, that means base 10. And then we're going to write parentheses because, again, the brackets in this special case are part of the notation. We're going to plug in the hydrogen ion concentration and we're going to enter 0.005 into the iPhone and then press log base 10, and we get a negative number. I'm just going to round off to negative 2.3. So the logarithm became that number there, but because it's a double negative, and we should put squiggly lines here, because it's a double negative, it becomes positive 2.3, and that is the answer. Now, pH has no units. You don't have to worry about any units of measure here. Usually when you're calculating a logarithmic value, you don't have to write units. So again, we use parentheses here because the brackets are technically part of the notation. Let's try another problem. So here the hydrogen ion concentration again is given. Let's calculate the pH. It's defined as the negative log of the hydrogen concentration in moles per liter. We don't see a base on the logarithm, but remember that means that it's a base 10 logarithm, and we're going to plug in 0.00002 for our hydrogen ion concentration. And in my calculator, I'm going to enter 0.00002 and then the log base 10 button. And I'm going to round that. And it's a double negative, so it becomes positive 4.6999. Now again, the reason for that negative in front of the logarithm is so our final answer will be positive. We don't want to have to deal with the negative number when finding pH. So I want you to go ahead and try number 31, and when you come back we'll do it together. Okay, we're back. So again, pH is defined as the negative log of the hydrogen concentration. And if you don't see any base on the logarithm, it's assumed to be base 10. And the hydrogen ion concentration is 0.000000049. So I'm going to enter that in my calculator, 0.1234567 zeros, and then 49, and then log base 10. And we get a double negative as usual, but 7.3, and I'm going to round off to just 7.3. A double negative becomes a positive, and there you go. So these two solutions here were acidic. This last one we just calculated is slightly basic because it's above 7. Remember, a pH of 7 is neutral. It's just normal water in terms of the hydrogen ion concentration. So if you got that one right, good job. Okay, go ahead and try number 32, and when you come back we'll do it together. Okay, we're back. So again, we need our basic definition of pH. It's the negative log of the hydrogen concentration, hydrogen ion concentration in moles per liter. We don't see a base on the logarithm, but that means it's base 10. And we just plug in our hydrogen ion concentration and go to the calculator. If you're using a graphing calculator, you're going to have to enter the negative symbol and the logarithm first. But if you're using an iPhone, you have to enter the inside part of the logarithm first. So I'm entering 0.0031, and then I'm going to press log base 10, and I get negative 2.5. I'll just round it off to negative 2.5, and then that's a double negative, so it becomes positive 2.5, and so that's another acidic solution because it's the pH is lower than 7. So if you got that one right, excellent. So now we're going to go backwards. In these problems, we're given the pH and we're asked to find the hydrogen ion concentration. So we know that pH is equal to the negative log base 10 of the hydrogen ion concentration. And in this problem, we're given the pH. The pH is 8. But remember, we can't really do anything unless we know what the base is of the logarithm, and there is no base. There's no base written. But remember, if you don't see a base, that means it's base 10. So now we need to isolate the logarithm. The logarithm is not isolated because this negative is there. So first we need to multiply both sides by -1, and I'm going to show that. It's a basic operation, but just so students don't get confused, I'm going to show that we're multiplying both sides by -1. It's little details like that that will tend to confuse students sometimes. So then we get -8 is equal to log base 10 of the hydrogen ion concentration, and at this point there's really nothing to do. We're stuck unless we can translate to an exponential equation. So the hydrogen ion concentration is equal to 10 to the -8. Zero 0.00000001 moles per liter. So that is the hydrogen ion concentration, and you can see why we don't want to use these numbers to measure how acidic a solution is. It's much easier to write 8 rather than this number here. So let's try another one of these problems. The pH of a solution is defined as a negative log of the hydrogen ion concentration. The pH is 5.71. And so the first thing we need to do is isolate the logarithm. It's not isolated because there's a negative in front. So we're going to multiply both sides by -1, and we get -5.71 is equal to log, and we need to know that this is a log base 10 expression. So at that point we're stuck unless we know how to convert from a logarithmic equation to a exponential equation. So we're going to use base 10, and the exponent is whatever the logarithm is equal to, and whatever's in the log function goes on the other side. And now we need to use the calculator. So on the iPhone, I'm going to enter 5.71, and then the plus minus button at the upper right, that changes it to negative. And I'm going to push the 10 to the X button at the upper middle right, and I get a very small number, 0.0000199 and I'm just going to round off to 195, and that is moles per liter. Let me shrink this over here, and we'll write moles per liter. So again, you can see why we don't want to use these numbers to measure how acidic a solution is. They're tedious to have to write. So now it's time for you to try. In number 35, the pH is 2. So go ahead and attempt 35, and when you come back, we'll do it together. Alright, we're back. So the definition of pH is a negative log of the hydrogen ion concentration. We know the pH is 2. They tell us that in the problem. We're going to multiply both sides by -1 to isolate the logarithm. We cannot translate that logarithm unless we isolate it first. And now we need to know the base of the logarithm, because the base is not written. We don't see anything there. But remember, if you don't see anything, it must be 10. So now we're going to translate this logarithmic equation to an exponential equation. The base is 10. The exponent is what the logarithm is equal to. And 10 to the -2 power is 0.01. And remember to write moles per liter. And again, remember those brackets are part of that that notation for hydrogen ion concentration. So if you got that one right, good. Okay. And try number 36. When you come back, we'll do it together. Okay, we're back. The pH is defined as this expression here. We know the pH is 10.3, and we know the base is 10, because if there is no base written, that assumes that it's 10. We're going to multiply both sides by -1, putting the negative on the other side of the equation because we have to isolate the logarithm. So now the logarithm is isolated. It's by itself on one side of the equation. Whenever you run out of room, don't panic. You can just go up here. Be sure to indicate with an arrow where you're going. So the base is 10. We're translating to an exponential expression. The base is 10. The exponent is -10.3. And whatever's inside the log function goes on the other side. So on your calculator, we're going to write 10.3, then the plus minus button at the upper right if you're using an iPhone. Then the 10 to the X button at the upper right, and we get 0.0000000, and 2 more zeros. So that's a really big number, actually a really small number. What I mean is a lot of numbers to write. So again, you can see why it's so much easier to use base 10 logarithms. And that is moles per liter. So moles per liter. If you got that one right, excellent. Okay, so the last thing we're going to do today is the magnitude of an earthquake. We're going to do another application of base 10 logarithms. earthquakes are hard to measure. When you have an earthquake over here, we call that the epicenter, where the earthquake is, where it originates from. And earthquakes are measured 100 kilometers from the epicenter. At least that's the reference distance. And a seismometer is a sheet of paper that goes around on some sort of spindle, and it draws on that spindle, and if there's an earthquake, there's a disturbance on the seismometer, and I'm sure you've probably seen that on science education programs and whatnot. Well, the length of the disturbance tells us how big the earthquake is. And what you'll find is it's very difficult to measure the size of an earthquake just by using this information here. The numbers, just like hydrogen ion concentration with pH and acidity, those numbers are very difficult to work with. So instead we convert to a logarithm, and guess what the base is going to be? It's base 10, because that's the foundation of our number system, 10 symbols. So the length of the disturbance is always measured in millimeters. That's important. And we don't have time, or really the necessity, to go into how the magnitude of an earthquake is defined, but it's just a definition. It's defined as log base 10 of 1,000 times the length of the disturbance measured in millimeters. So that's this x value here. And again, you don't really have to know where that, what that, what the logic is behind that definition, but it's based on a comparison between the normal earthquakes that we see and the change when you have a disturbance. That's where that 1,000 comes from. So let's do some practice problems here. We're going to try to find the magnitude of an earthquake that has a 0.1 millimeter disturbance on a seismograph. The paper itself is called the seismograph. So remember, the magnitude of an earthquake is defined as log of 1,000 times the length of the disturbance. And whenever you don't see a base, that means base 10, right? Now I'm going to switch to brackets because we're going to have two sets of parentheses here. I don't want to confuse things. So we're going to plug in 0.1. And then we get log base 10 of 100. And we can actually calculate what that is without using our calculator. Remember, you can just convert that to an exponential equation. 10 to the x power is equal to what? I should probably use y instead of x. Y is what this whole logarithm is equal to. Well, obviously it's just 2. Now you can do it on your calculator if you want, that's fine. But you can see the magnitude of the earthquake is 2. And remember, when you're calculating logarithms, we typically do not write units. There are no units for the result when you compute a logarithm. So it's a magnitude, has a magnitude of 2 on the Richter scale. That's what the logarithmic scale is called, the Richter scale. So now, and by the way, that's a very small earthquake. The biggest earthquake that I think I've experienced is about 6, maybe 6.5. That's a very, very large earthquake. So let's try the next problem here. The magnitude is equal to log of 1,000 x. And when you don't see a base, that means base 10. We're multiplying 1,000 times the disturbance, the length of the disturbance. So we need to find log base 10 of 8,000. So in my calculator, I'm going to enter 8,000 and then push the log base 10 button. and we get 3.9, and I'm just going to round it off. So 3.9 is a bigger earthquake. We have a bigger disturbance, much bigger, on the seismometer, but it's only a 3.9 earthquake, so that's not a very big earthquake. Let's try one more of these. Now we have a very large disturbance on the seismometer. And 40,000 milliliters, let's calculate what that would be in feet. So that would be about 120 feet. So realistically, you can't calculate, you can't measure that on a seismograph, a seismometer, because it's doubtful there's going to be a seismometer that's that big to even measure an earthquake like that. So people who measure earthquakes, they would have to come up with some other method. But we can do the math, assuming that there were an instrument that could measure this. So we're going to plug in 1,000, or plug in 40,000, that is. 1,000 times 40,000 is equal to 40 million. So we have log base 10 of 40 million. So I have 40 million in my calculator, and I'm going to press the log base 10 button, and we see that that's approximately a 7.6 earthquake. Now that's a huge earthquake, very large, so big that most instruments probably won't be able to even measure that. So I want you to try number 40, and when you come back, we'll do it together. All right, we're back. Okay, so we're just going to plug in. First, we're going to define what the magnitude is. We're going to figure out the base. If there's no base written, then that means base 10, right? So we're trying to find log base 10 of 178,000. So I'm going to enter 178,000 into my calculator and press the log base 10 button, and I get 5.25. So that's a big earthquake, but it's not going to cause complete destruction necessarily. As the magnitude of an earthquake goes up, the actual feeling that people would get when that earthquake happens really goes up exponentially. So the difference between a 5 and a 7 is a lot larger than we would think. That's the only problem using these numbers, is that they're kind of deceiving. Okay, go ahead and try number 41, and when you come back, we'll do it together. Okay, we're back. So the magnitude is defined as log base 10 of 1,000 times the length of the disturbance on a seismometer. And we don't really need brackets until the next part of the problem. So we're going to plug in our disturbance on the seismometer, which is 10 millimeters. So we get log 10,000. So we could actually calculate this without our calculator. This is 10 to the 4th power. So it's just going to be a magnitude 4 earthquake. But if you want to enter it into your calculator, enter 10,000 into your iPhone and push log base 10 and you get 4. Again, with your graphing calculator, it's going to be completely different. If you got that one right, good job. Try number 42. When you come back, we'll do it together. Okay, we're back. So this is a 5 million millimeter disturbance. So that means that there's really no instrument that's going to be able to measure this, and the earthquake is going to be so big that we're all in a lot of trouble. Okay, so enter in 5 million and multiply that by 1,000, and we get 5 billion. So I'm gonna have to enter in 5 billion to my calculator. Then I'm going to push the log base 10 button, and we see that this is a very big earthquake. It's a 9.6. I'm just going to round off to 9.7. So that earthquake would probably destroy a city. It would easily destroy a city. So if you got that one right, excellent. Okay, we're just going to do a couple more problems here. Now we're going backwards. We're given the magnitude of an earthquake, but we're asked to find the disturbance on the seismometer. So M is equal to 6.3. We don't see a base, so we know the base is 10. We need to translate to an exponential equation in order to help us figure out what's going on here. And then we're going to calculate. So we're going to enter 6.3 in the iPhone, then push the 10 to the X button at the middle, upper middle, and we get 1,995, actually 1,995,262, roughly. Divide both sides by 1,000. And our final answer is, maybe we should put squiggly equal signs there. Final answer is 1,995.262 millimeters. So that's a pretty big earthquake. 6.3 is a very, very large earthquake. Alright, so again, we're just going backwards here. We're getting some practice with the meanings of all these concepts and the definitions. So the magnitude of an earthquake is defined to be log of 1,000 times the disturbance on a seismometer. We know the magnitude is 3. And we know the base of that logarithm is 10, because if there is no base written, it must be 10. That's just notation. Then we're going to translate to an exponential equation. 10 to the third power is 1,000. Divide both sides by 1,000, and x is equal to 1. So it's actually 1 millimeter, a 1 millimeter disturbance on the seismometer. So why don't you try number 45, and when you come back, we'll do it together. All right, we're back. So the magnitude of an earthquake is defined like so. The magnitude, we're told, is 4.8. And if we don't see a base there written in a logarithm, we know it's base 10. Now we just translate to an exponential equation. And in my iPhone, I'll enter 4.8 and then push the 10 to the X button in the middle, and we get 63,095.7 approximately. Divide both sides by 1,000, and we get 63.0, and maybe I'll just round off to 63.1 millimeters. Be sure to write your units. That's the approximate size of the disturbance on the seismometer. If you got that one right, excellent. Go ahead and try number 46, and when you come back, we'll do it together. All right, we're back. So the magnitude of an earthquake is defined again as log of 1,000 times the disturbance on a seismometer, the length of a disturbance. This is a very large earthquake, magnitude 10. We don't see a base on that logarithm, so we know it must be base 10. Translate to an exponential equation. The base goes there. Whatever the logarithm is equal to goes there. And so 10 to the 10th power, well, that's going to be a very large number. It's a 1 with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 zeros. So that's 10 billion. And then if we divide by 1,000, that's going to be 10 million. So 10 million millimeters. And if you convert that to feet, you can see that that earthquake would probably destroy the whole world. If we convert that to feet, we would probably, that'd be roughly maybe 30,000 feet disturbance. So the world would pretty much be destroyed. So we got that one right. Good job. Okay, that was the class today. If you'd like to take screenshots of all the work that we did to help you with your homework or to study for tests, go ahead and do that now. Here's screenshot number 1 and number 2. And number 3 and number 4 and number 5 and number 6 and number 7. But don't go before you get your homework. Let's take a look at the homework. Here's the first screenshot of the homework. And here's screenshot number 2 with the answers. Remember, if you don't do that homework, it's a 100% guarantee you're going to learn absolutely nothing in this entire course. So get that homework done, and I'll look forward to seeing you in the next class.